Assalamu alaikum dear student, this is Vaidisha. To continue with the video sessions of the first term course, today we will be discussing the torque on a current carrying coil in a magnetic field. Let us draw the diagram that we have north side of the magnet, this is south side of the magnet, and we have a coil placed in the magnetic field produced by this magnet. Direction of the magnetic field is towards the south of the magnet. This is P, S, Q, R. So this is coil P, Q, R, S, where this side is of length A and this side is of length B. So if a current carrying rectangular coil is placed in a uniform magnetic field, it experiences a force and a torque. Let us consider a rectangular coil having n number of turns carrying current I in a uniform magnetic field of flux density B. This is B, magnetic field, which is uniform magnetic field. Each side P and S, PS and QR of the coil experiences a force as shown in the figure on the board. The effect of these forces is to try to compress the coil. These two sides experience a force, and because of that force, the coil is not actually compressed, but the forces actually try to compress the coil, but as the coil is rigid, so they cannot do so. The force F acting on the side PQ and RS, again these two sides again experience forces. PQ and RS, SR sides experience forces due to the magnetic field available already and another in a magnetic field produced by the current flowing through the coil. The force acting on PQ side is opposite to the force acting on SR side, according to right hand rule. So, this force F1 and this force F2, two forces. The force acting on PQ side is, for example, into the board, and the force acting on this SR side is out of the board. So they are acting in opposite directions on the coil. And the magnitude of the force is already given by F1, this one, equal to F2, equal to common F, and the magnitude is N B I into A. F1 magnitude is equal to F2 magnitude, and combinedly they can be given the name F, and the magnitude is already calculated in the previous topics, that is NBIA, where N is the number of turns of the coil, B is magnetic field, I is the current, and A is the length of the wire. Now we are going to find the torque, which is equal to R cross F, or simply RF. For simplicity, we take simple RF, where R is the moment arm and F is the magnitude of the force acting on this coil. So, for this reason, in this equation, we know the value of F, but we are going to find the value of R, the moment arm. To find the value of R, let us consider another diagram which is taken from the top view like this. For example, this is the top view of the coil, this one. This is the axis of rotation, the central point. Force F1 is acting in one direction. This force is shown in a top view like this, and this force F2 is shown in the top view like this, F2. So, as we know that this is the length B, so moment arm is the perpendicular distance between the line of action of the force and the axis of rotation. So if this is B, so this force and this will be the moment arm. So R is this moment arm, which is equal to B cos of theta, and value of F is NBIA. So putting these two values in this equation, we can find torque, NBIA, B cos of theta. Finally, torque is equal to NBI and the product of AB. This is A and this is B. So, multiplying these two sides, side multiplied by side, is equal to the area of this whole coil. So we can write capital A, which shows the area of the coil in cos of theta. This is the topic, torque is equal to NBIA cos of theta. We have another methods of deriving the same equation, but we'll simply follow this one as it is given in the textbook. Thank you. Have a nice day.